Hello. Sorry, I need a second. Let's do number 4. Okay, after falling from rest at a height of something, a ball with a mass bounces up, reaching a height. What? It says kinematics and Newton's second law, but it sounds like a momentum impulse problem. What? Okay, let's draw a picture. When in doubt, draw a picture. So we were at rest, and then we fell 30 meters. And then we bounced upward, reaching a height of 20 meters. When we were at the ground, that lasted 20 milliseconds. Find the average force using kinematics and Newton's second law. So Newton's second law says F equals ma. Well, more specifically, it says the sum of the forces equal ma if the force and the acceleration are in the same direction. Okay, so we didn't bounce up as high. We only bounced up to 20 meters when we started at 30. So we lost some energy. So the ground did apply a force, a staying near the ground kind of force. So the acceleration and the force must be directed downwards in order to keep us from bouncing up as high. Kinematics makes me think we need to calculate this acceleration. I want to use momentum and impulse to calculate that force, though. Use kinematics first. So kinematics says if we have initial velocity and final velocity and acceleration, time, and a change in displacement, as long as we have 3 of these things, we can calculate a fourth. That will always be true. So do a bunch of kinematics first. Okay, so we started from rest, and we fell from a height of 30 meters. We don't know how long it took. Oh, when we're falling, acceleration is gravity, so that's just 9.8. So we have 3 things. We could calculate a lot of things. We could calculate how long it took to fall. I don't think that matters. We can calculate the velocity going into the contact with the ground, which could be useful, I guess. So let's find that. All right. Here are kinematic equations as remembered by me. I know final velocity squared equals initial velocity squared plus 2a delta x. I know change in displacement equals v naught t plus 1/2 at squared. That's a half. And I also know final velocity equals initial velocity plus at. Those are things that I know. Those are the kinematics equations. We're looking for one that doesn't have t because we don't have t and we don't really care about t. Let's use the squared e one. Okay, so final velocity squared equals initial velocity squared plus 2a delta x. We're solving for final velocity. Initial velocity is 0. When you square 0, it's still 0. 2 times 9.8. And we went 30 meters. So 2 times 9.8 times 30. If we take the square root of that, nope. If we take the square root of that, it ends up being 24.2 meters per second. I still don't know where this is going. Okay, so I know when we were about to hit the ground, we had a velocity of 24.2 meters per second. And then a force was applied, and we had less velocity. That's something I know. A bunch of kinematics. A bunch. Okay. So on the way up, I know. We eventually, on the way up, reach a height of 20 meters. Acceleration is still pulling us down at 9.8. When we've used up all our oomph from the ground, our new final velocity is 0. If that's a maximum height, that means we use up all our velocity, and our velocity is 0 at the top there. So we could calculate our velocity going into that. Oh, acceleration is a change in velocity. Oh, okay. I know where we're going now. Okay, so we need to find the velocity at the beginning of the up part. It's not exactly 24.2 because we know a force was applied by the ground. So we lost some velocity. So we need to figure out how much. So in order to calculate final velocity, I think we should use the same equation because we still don't care how long that took. Oh, and I'm not articulating what I'm doing. So 0 squared is still 0. We're solving for final velocity. Acceleration is 9.8. In my class, in your class, your teacher might say to use 10. So I'm going to do 2 times 9.8 times 20. I'm going to take the square root of that. So velocity on the way up is 19.80 meters per second. Slower than before, which we would expect. Okay, I really think we have to use momentum here. But they say no, apply Newton's second law. Newton's second law says F equals ma. We have the mass. The force, let's draw a free body in that moment in time, just in case it reveals something. I know we have the force of gravity going down. Your teacher might call that mg. We have a normal force from the floor, which must be more than mg if it's like applying some sort of force. There's no formula for normal, so we can't like calculate it. You just have to like subtract other stuff. You know what? It shouldn't be bigger because this force is accelerating us down somehow. So I wonder if there's like friction from the floor. That's mu normal. We don't have a mu. We can't calculate the normal without other stuff. I don't want to use Newton's second law. I want to use momentum. Let me show you the momentum way to do this. Momentum says impulse. Impulse. The symbol is J. I call it Jimpulse. Impulse is a change in momentum, which means final minus initial. The final momentum is mass times velocity. So mass times the final velocity minus mass times the initial velocity. And impulse also equals force times time. So if you factor out the m, this is just final minus initial. So I'm going to say m delta v equals ft. That's a true statement. Doing impulse momentum calculations, it sounds like that's not what your teacher wants you to do, but that's the only way I see how to do this. So the mass is 0.5. The change in velocity is now the direction matters. It doesn't really matter which one you call positive, which one you call negative. A lot of teachers say down is negative and up is positive. I don't really care. I don't like negative numbers, but whatever. So the change in velocity has to take into account that we're also changing directions. We're not just slowing down from 24.2 to 19.8. We're going from 24.2 to 0, changing direction, and then going 19.8 the other way. So the change is 44 meters per second. The force we need for F equals ma, yeah, we don't have force. And the time is 20 milliseconds. Milli means thousand, so 1, 2, 3, so that's 0.02 seconds. Okay, one equation, one unknown. I'm not sure about this. Final, it's 19.8 minus a negative 24.2, so that means add, yeah, so that is a 40, okay. Times 0.5 divided by 0.02. So our force is 1100 newtons. So now I can use Newton's second law. F equals ma. The force from the floor is 1100. The mass of the ball is 0.5. So acceleration would be 1100 divided by 0.5. That cancels out. Divided by 0.5. I think the acceleration could be 2200 meters per second squared. Oh, find the average force. Never mind. That is the force. That's finding the... So I never used Newton's second law, even though they said to use Newton's second law. How could you use this? So, mass is 0.5. I never found an acceleration. The acceleration's 9.8. I guess in this moment, acceleration is change in velocity over time. Maybe that's what they want. So we do 19.8 minus negative 24.2 divided by 0.02. 19.8 minus negative 24.2 divided by 0.02. That acceleration is 2200. So that times 2200 equals 1100. Hey, that's the same thing. I'm feeling really good about 1100. And we also found it using Newton's second law, which is what your teacher wanted. Job well done. We got this.